Let's now compare. This is equivalent static, this is response spectrum, this is linear time history, and you see linear methods. So I already told you linear, this one is input is code factors, model is linear, modes are fundamentally only one fundamental mode, output is one set, assumed by, signs are assumed by the engineers. Whether you apply the earthquake to the left or the right is assumed by you. Earthquake is not defined. You say, oh, I'm pushing, my force is going, I like, some people like to apply from left to right, some people like to apply from right to left. So they get negative moment, they get positive moment. So it's that simple. Then you have to use those combinations to correct for those signs. And then response spectrum, this is a spectrum. We do not use those factors. And then we have linear, everything is nearly similar. But instead of one mode, we have multiple modes now because we add them together. We get the peak values and then combined by sign is lost because of the combination of the square. When you did the square and root, sign is lost, as you can imagine. And then time, no information, and lost in modal combination. This one gets much better. You have all the things here, except that it's linear. Otherwise, this is pretty good. So if the structure is expected to be linear, this will be good. So you get equivalent static, you have this distribution predetermined, and for response spectrum, it is coming from the modes, and from time history, you get every individual floor displacement as response. Okay. So very clear how each one will give you the output. This is very important for design. I will come back to this when we do the ETABS. I don't want to mix the design and analysis part at this time. So I will present this important slide again. So forget about this for now. So nonlinear, now let's go to the last one. Now let's go back to the comparison with linear and nonlinear. So this is the starting preliminary design, response spectrum for initial design, then push over to check the mechanism, what is happening to the structure, and finally nonlinear time history analysis to check everything. So if you do the design seriously, you have to actually do all of them. You cannot ignore, as you go forward, you have to do everything behind also. And that's why when you normally come, you have a very good understanding of the structure. What did the code say? What did the response spectrum say? What did the linear time history say? So you can compare everything on 4 or 5 different methods, get complete understanding of everything. What changed from here to here? Why? Right? What did I not capture here? Because you can plot the base shear comparison, you can plot the story displacement comparison, you can plot the story drift comparisons for different methods, and you can compare them very easily. So it gives you a complete understanding of the structure. And this is now required for very tall buildings. And also now it's becoming more and more common by the owners and clients. Because you might have seen one of the posts, why is my structure safe? This question cannot be answered without nonlinear time history analysis. Because every other method cannot answer this because it's based on assumptions, unrealistic, most of them. So if somebody really wants to know the answer, is my structure safe for this particular earthquake or this location or this one, then you need to go there. So that's the quick one, preliminary sizing, response spectrum, push over, nonlinear time history, visually showing you how this happens. This is the important thing to remember now, concluding slide. Summary of everything on one slide. Everything that we have discussed in 3 classes is on this table because it tells you the method and it tells you what effects it captured and what it missed, right? And this is a very good way to compare and represent things. When you do your thesis, normally, you should compare your literature review in the same way. Different papers, what they compare, what they missed, and what are you doing. So you should be on the right-hand column saying, oh, I'm doing everything that everybody missed. Then you will have a good thesis. So it's a very good framework to show what you're doing and what others have done and what is missing. Okay, so let's look at this. So first of all, you can read the table vertically, or you can read the table horizontally. For example, higher mode effects, who takes care of it and who misses it, right? Similarly, equivalent static, what does it do? What does it miss? So it doesn't do much in terms of the advanced things. It just does the minimum thing. So model complexity is low, runtime is in seconds, but it misses all these important things for a tall building. So for tall buildings, we never use it. That's the conclusion. That for tall buildings, if you're using equivalent static method alone, not acceptable because it missed everything. So that's the conclusion. Response spectrum, it included higher modes but missed everything else. Okay, fine. So we at least have the higher modes here. So response spectrum is better than that. We will use it. It's low, also takes in seconds. Linear time history captures a lot of the things that we saw earlier. Now the complexity is medium because you have to get the ground motions, you have to scale them up, you have to add them, run it, more results to process, takes minutes to hours. Pushover considers more, and some things it considers partially. You can, depending upon which pushover method you use, because there are so many. So linear time history is only one. Response spectrum is only one, but this is many. So that's why it depends on the method. And then it considers many things, but start to lose here. But now it may take minutes to hours. And then finally, nonlinear time history analysis captures everything. That doesn't miss anything. But it can take hours to days, to months, actually, used to take months. I remember we did one project, it took 2 months of continuous running to complete one run. 2 months. Yes. 2 months of program running on the machine to get the results. Okay, so this is this will immediately tell you what method you need if you're looking for a certain thing to be included. This is for tall buildings, not for ordinary buildings. Ordinary buildings is different table because all of these things are not relevant to low-rise buildings. Okay, higher mode effects. This is important. I told you the response spectrum is, these are two very different response spectrum, by the way. This is a typical response spectrum from most countries. This is Bangkok response spectrum. This is Manila. So my response spectrum from Bangkok is very funny. It's very funny because it peaks here. Most response spectrum peak in the beginning. And this is because of the ground, the soil is the rock is very far. So there is a basin effect. Because of that, even the ground motion is very, in the beginning, the first period starts because soil is already there. So the soil period also needs to be added before we reach the structure. So that soil is also moving slowly. And so that natural period of the soil between the rock and the structure makes this effect. So this is the response spectrum. But the important thing is here. This is, let's say, the first mode, 5.6 seconds for a 50-story building. And the modal ordinate is very small, 0.1 something. So that means 50% of the mass will be multiplied by 0.1 ordinate to get the force. Second mode is 30%, has 30% mass participation. So now the ordinate has become higher. So now this one will come here, and now 0.25 will be multiplied by 30%, and then so on. So this is that means each mode, when it goes to the higher mode, the modal participation drops, but the response spectrum ordinate increases, right? So the response spectrum method takes into account this thing by using the combination rules and all. but it misses the contribution of individual modes because it doesn't account for them individually. They're just added together. So it considers the higher mode effects, but the unique, I'll show you in a minute, unique pattern is gone. And there is a reason why that will be important. So here, but for Bangkok, these modes have different story. If you have a 20-story building, 25-story building, then you can see that for Manila, higher modes are increasing the contribution. For Bangkok, they are decreasing the contribution. That means here, first mode, 25-story building, 30-story building in Bangkok is the most critical one. And lower rise are not so critical, whereas in other countries, low rise buildings are more critical. Right? So this is a very unique, but you can read everything from the plotting the natural period on the response spectrum to understand what's going to happen, and the modal participation factor over there to understand the full picture. Okay, but response spectrum takes this into account for the total effect, but misses the local effects, and especially when it comes to nonlinearity. And that's the point that I want to make. So please watch carefully the next one. So this is linear response, mode 1, mode 2, mode 3, mode 4. So now if you do modal separation, that means you look at the response of each mode before they were added and plot them, you will find a very different story. For example, here, this is the story moment. So the black line is the summation of all the modes using the response spectrum, right? Mode 5, blue line, is actually like this for the moment. So you can see that for this mode, the moment was very high in the middle of the building and very low at the bottom. Normally, we assume that the moment should be very large at the base and small at the top, and which is true. The total moment is like that. But the individual modes, you can see 5, and look at the mode number 3, mode 4. These are giving very different pattern of moments, right? And if you are covering them all by the black and you're using linear design, it won't matter because you designed for this one anyway, because the quantum spectrum gave you that. And you use, that's okay. And then story shear is even stranger. Story shear for these modes, very high. Top 30 stories, suddenly the shear become very large. This is quite unusual because you assume that this story shear will be the similar pattern as the moment, and it will be high at the bottom and 0 at the top. But that's not true. Actually, the story shear gets a high value at the top of the building. And many engineers not familiar with tall building start to reduce column size or shear wall thickness as you go up, or start reducing the concrete strength as you go up. And suddenly you have this high shear problem, right? So far, because the black line is beyond that, so if you use response spectrum, you still captured it. But the problem comes in so this is the same thing, drift, similar, you captured, but the patterns are very different. What we need to recognize is that each modal response is very different from the other, and the response spectrum just covers it up and shows us a very wrong picture of this plot. This black line means that you think that at 25-story, all the modes are giving similar values and you're adding them together, but their addition here and their addition is here. Here is just one mode doing everything. Here it is the other mode. Because we are just adding them together, we don't see the picture. But why it is important is when we go to nonlinear response. Because I wanted to save it but anyway, nonlinear response, the linear response, we take the linear response and we divide it by R. You remember that factor, right? You reduce it by a response reduction factor, let's say of 5 for a tall building. So you reduce all the modes, because all the modes are added together, you reduce them by the same factor by 5 to go from linear to nonlinear estimate. But what really happens is that the higher modes do not yield. Nonlinearity is only going to happen in first mode, which is at the base, which is because of the moment. So higher modes are not going to yield. Structure will be elastic for higher modes because their frequency is very high and they're deforming in a pattern for which you have not provided any hinges. So which means they should not be reduced by the same factor as you did for the response spectrum, which was the total result. So you completely missed the individual higher mode effects and reduced them by the same factor, whereas they should not have been. And now you can look at this one. Forget about the moment. I want to show you in the shear. So this is the blue one is the elastic demand coming from response spectrum by combining all the modes that you saw last time. The red one is the true demand coming from time history, nonlinear time history analysis. And the green one is the demand reduced from linear to nonlinear by dividing R. So for the first mode, everything looks beautiful, perfect, because that is the elastic demand, that is the reduced demand, and this is the actual demand. Actual demand is still higher than the reduced code design. Code design is green, so you're fine, right? No problem. Go to this one now, and this one now, here and here. Here, let's say, look at the fourth mode, for example. Fourth mode, now the green line and this one here, yeah, here. This one, even in the second mode. Now you can see here that the true demand is already less than what the code is giving you. So which means the code is now underestimating the capacity. So true demand is here, and then the elastic demand is here. So now they are very close. Here you had the R of full R here, right? 5 or 6 minutes. Here the R is now not there anymore. And here the R is not there anymore. So now the code is giving you a very small design demand, much smaller than the real one. So which means now you're going to be in trouble because this one is close, is okay, but this one is very far. So you design for this one because you divided this one by R and you went there, but actual is here. So now this is much higher than the design. So which means the shear is now, higher mode shear is now over reduced. The actual shear demand will be much higher than the design demand. Very unsafe. Nonlinear time history analysis. We assume that nonlinear time history analysis, we just concluded in this chart, this one, that it does everything, the green. So that's assumed to be the true demand because there's no other way to do that. So we assume that the nonlinear time history analysis is giving us the true demand. So now you can see here that now we are very far from the true demand. And this elastic and this one very close. That means no nonlinearity. And here, even worse. The true demand is higher than even the elastic demand. So this here also, here. So there are going to be portions of buildings where first of all, there'll be no yielding and there should be no R, or R should be less than, or just 1 or very small. 3-4 PhD students did a lot of work to find out. They did a lot of results, and then that's how the code in Thailand is going to be changed. And many people are realizing that you cannot reduce all the modes by the same factor. So now they're coming up with different R factor for different modes, and then you add them together. So that's the higher mode effects, and this is one of the reasons that this building had a problem. Higher mode effects, shear being much larger than the design shear because they reduced it by the same R.